This video is about convolutional neural networks. So the goal is to see how we can take advantage of some of our visual system's features in artificial neural networks. In the last video, I talked about some features of the visual system, that being its retinotopic, which is going to be the substance of convolutional neural networks, among some other features. Let's focus on what is relevant to convolutional neural networks. So inspired by the brain's topological or retinotopic connectivity, and in an effort to reduce the number of connection weights that need to be learned, scientists and computer scientists have devised the convolutional neural network, or CNN. So let's review what convolution is first of all. So in the continuous domain, convolution between two functions f and g, which for the purposes here I will say map from R to R, is written f star g, and then it's a function of some variable. It's an integral from negative infinity to infinity of f times g of x minus s ds. So notice that here we have the s is positive here, but it's negative here. So convolution, basically, it's an integral of a product between two functions, and you basically take one function and you reverse it. You shift it and reverse it, and then you take the inner product. Anyway, we won't dwell on that too much, but technically convolution involves reversing one of the two signals. Now in the discrete domain, so if you have an image or a vector or something, you can also talk about convolution. So in this case, f and g are both, let's say, n vectors. And so f star g, which will be indexed because it'll be a discrete output as well, is a sum from n equals 0 to n minus 1 of f sub n times g m minus n. So again, we traverse the spatial index, if you like, forward in one and backwards in the other one, but it's not a huge deal. So what does that look like in terms of images? So now these, I showed the continuous and discrete convolution operators for 1D, but you can just imagine what they look like in 2D. Now, here I have an image on the left here, and I've got a convolution kernel. So this is the image, which I'll say is F. And this is the convolutional kernel, G. And I'm going to convolve those two and get an output image. So this thing on the right here is what I would get if I convolved that image with that convolution kernel. So that convolution kernel basically means you set it down in a whole bunch of different areas, or you slide it over the image, and every place that it lands, you take an inner product between that part, that window of the image, and the convolution kernel. And then you take the value you get and you assign it to the center, the pixel that's at the center there. So I don't know if you saw me draw this thing here. Okay, so in this case, this particular kernel, convolution kernel, has got like a bright spot on one side over here and then a dark spot on the other side. So it's actually looking for edges that are oriented at 45 degrees. And it will respond either positively or negatively, depending on whether it's going from bright to dark or dark to bright. So let's say we're to put the kernel up here. You can see how it goes from dark to bright. And that's why when we get a bright edge over here. Okay, so I think you can get the idea. It's basically running this template over sliding it over your whole image and computing the response and assigning that response to the center pixel in the output image. So what we get over here, we call a feature map. or it's sometimes called an activation map. And I guess we can call it H. Okay, so in 2D, convolution looks like this. Discrete convolution is F convolved with G. Now we'll have two indices because there'll be like a row and column. It's a double sum over indexes I and j of Fij times G m minus I n minus j. Okay, or now this is the way we'll normally use it in neural networks. Is we don't really do the true convolution where you flip the kernel backwards. So we'll usually use it more like this, and I'll use a slightly different symbol. I'll put a circle around the convolution operator, and it'll be again a double sum Fij times G I minus m j minus n. Okay, so that's what convolution is, and convolutional neural networks use that sort of operation. The kernels here, these are essentially the connection weights, if you like. And what you do is you define a whole bunch of kernels, and they're like different feature extractors for extracting different oriented edges or different types of templates or shapes from your image, detecting those matching features in your image. Okay, a joke first. I want to die peacefully in my sleep, like my grandfather did, not screaming in terror like the passengers in his car. Okay, now I have this slideshow that a colleague made a number of years ago about convolutional neural networks. So let me step through this and sort of outline some of the details about convolutional neural networks. So in the past, what we do is you take, let's say you've got a 32 by 32 input image. Maybe it's 3 color channels like red, green, and blue. So in total, that's 3,072 different inputs. So what we would normally do is put it in a giant vector. Saying 3,072 by 1, but that's a column vector. I would put it, I'm showing it here as a row vector, but it doesn't really matter. You would multiply by the connection weights, W here, and then let's say we've got 10 output neurons over here. So our connection weight matrix would be 10 by 3072 or 3072 by 10 if you're doing row vectors. Looks like here this is a column vector. Okay, then you get your output. Now it's a bit different in convolutional neural networks. So yes, we do want to get the input current to these neurons in the next layer. Before we would get one number for each neuron, and it involves that number involves all 3072 inputs in or all pixels in your image. Basically the dot product. You have 10 different sets of connection weights, one for each of these nodes in the next layer. Now in convolution, it's a bit different. You keep, instead of taking your image and you make it a vector, you keep it in the shape of your image. And what you do is you convolve your image with a bunch of filters. So I've got a 3-channel image input here, and now I've got a 5 by 5 by 3 kernel. I'm going to convolve this kernel with my image. I slide it over my image spatially. So for any particular location of my kernel, I get one output number. I basically take a dot product of the numbers in my kernel with that patch of my image. It gives me that one number. And so I get this sort of thing. So W transpose now represents my kernel. X represents that patch of my image, and I have a bias as well. So for example, with my, how many weights do I have? If my kernel is 5 by 5 by 3 channels deep, that's 25 times 3 channels. That's 75 different connection weights, or kernel weights. And then I have one bias. So it's basically 76 different numbers that my neural network needs to learn. Because we don't, I guess I should say, we're not typically setting these kernels. We don't know what the kernels are going to look like. That's what we want our network to learn. We want to learn what kernels efficiently encode our image and allow us to do whatever things we need to do later on in the network. So here's just a quick animation of the kernel sliding over the image. You can see this is taking a 3 by 3 window. So the kernel is 3 by 3. And for each location of that kernel, we get one output sample. Now you'll see that this next layer here is only 5 wide, whereas the input is 7 wide. Okay, so that's going to be a recurring theme here. Okay, so we have our convolution layer. We have our input, and we convolve it with a 5 by 3 kernel or filter, and then we get a 28 by 28 channel or feature map or activation map that comes out of it. Typically, we'll have more than one kernel. In fact, almost always. I've never seen anyone not have more than one kernel. So here's a different kernel. It'll give me another channel in my next layer. And typically what you have is a whole bank of kernels, each one creating a different channel in the next layer. So in this case, I'm showing 6. So I had 6 convolution kernels giving me 6 different feature maps or activation maps in the next layer. So now you can see how this hidden layer is also, just like the input was a stack of a bunch of channels, and each channel was had this spatial image arrangement. Same thing with the next layer. Just like in the visual system, how each layer is retinotopically mapped from the layer below it, that being each neuron is affected by neurons that are sort of retinotopically local. You get a stack of channels that are, again, retinotopically local. Okay, so ConvNet is a sequence of convolution layers interspersed with activation functions. So we have a convolution with a bunch of, in this case, 6 different kernels, and then we run them through a ReLU to get our next layer, which is here. Now we run those through a convolution, 10 convolution kernels, and then run those through a ReLU, so we get the next hidden layer, which has 10 channels of activation maps. So just showing some quick examples. This is taken from VGG, which is a famous convolutional neural network that was trained on, I think, ImageNet. Yeah. Okay, so you can see what the kernels look like, and then the next layer up, the kernels are a bit bigger. Well, the footprints of the kernels are a bit bigger, just like I said in the visual system. Anyway, I don't want to dwell on this too much, but just to show you that there are pre-trained convolutional neural networks out there. Basically, when you have image input, convolutional neural networks are the state of the art. Okay, so let's take a closer look at the spatial dimensions. There's a 32 by 32 by 3 input image. We're convolving it with a 5 by 5 by 3 kernel, and we get an activation map that's 28 by 28. Now you can see, let's look at this example. The input image is 7 by 7, and my kernel in this case is 3 by 3. So if I can, there's one placement of the kernel. I can place it here. I'm trying to get my laser pointer. Place it here, but I can move it over one, place it here, move it one, move it one. And so you can see that there are 5 different horizontal positions and also 5 different vertical positions. So that gives me 25 total different positions for that kernel. That was with a stride of 1. Now with the stride of 2, we're going to move our kernel over 2 spots. And then we can move it 2 more spots. So we get we get 3 different horizontal and then 3 different vertical positions for a total of 9. So our output activation map would be 3 by 3. What about a stride of 3? We start here, we move over 3 to here. You can see that when we try to move over, we're going to run into a problem. So you can't use a stride of 3 in this case. It doesn't fit. So there's this handy little formula. I won't dwell on the formula. I don't particularly care that much. But if your input image is n by n, and your filter is f by f, and your stride is stride, then this gives you your output size. So for example, when the stride was 1, we get 7 minus 3 is 4, divided by 1 is still 4, plus 1 is 5. So anyway, it's just a handy little formula to figure out what your output size will be. But again, I'm not going to dwell on it. The important thing though is you get a non-integer dimension for your next layer if your stride and your filter size don't match up. Okay, in practice it's common to pad your input so that you don't have this issue, so you don't get smaller and smaller as you go on through multiple convolution layers. So in this case, for example, our filter is 3 by 3. We're going to pad everything by 1. That means you add a whole sort of outline of zeros, a whole bunch of pixels, and you just set them equal to 0, so that it makes sense to put your kernel up in the corner here. Before, we couldn't really put our kernel up in that top left corner. Remember, this here is our actual image, and we've padded it with zeros so that we could push our kernel up into the corner. So because of this, it allows us to create an activation map or feature map that's the same size as our input image. So we had a 7 by 7 input image, and if we pad by 1 using a stride of 1 and a filter that's 3 by 3, we can have the next layer again still be 7 by 7. Okay, so some other calculations I won't go through in detail. If you have a kernel of 5, you need to pad by 2, right? Because your kernel, when you push up into the corner, is going to extend 2 pixels out of your image. Okay, now if you don't do padding, and your kernel is quite large, in this case we're doing 5 by 5 kernels, your your feature maps get smaller and smaller. So you lose kind of, with a 5 by 5 kernel, you're going to lose 2 on each side, 2 pixels on each side, including top and bottom. So you go from 32 by 32 to 28 by 28. You're losing 4 pixels on all sides. And if you do that again, you're going to go down 4 pixels again on each dimension, so 24 by 24. So shrinking too quickly is apparently not very helpful. I don't have much experience in this field, but this is what I've been told by other people who do use convolutional layers quite a lot in their networks. Okay, examples time. So let's say we have a 32 by 32 image with 3 color channels, and we've got 10 kernels, and each kernel is 5 by 5 by 3. We're going to do a stride of 1 and a pad of 2. So as I have told you before, the output size is going to be still 32 by 32. And there's this formula. I don't really care about this formula. I'm not going to dwell on it. But we get a 32 by 32 size feature map, and we have 10 channels in it because we had 10 different kernels. 1 channel per kernel. Now, here's something I do want to focus on is how many, that's 10 different kernels, and they're each like kind of like 3-dimensional arrays of numbers. Isn't that a lot of parameters to learn? Because again, we have to learn these kernel values. Let's look at it. So if, in this case, we have 10 kernels. Now each is a 5 by 5 by 3 kernel. So remember, 5 by 5 by 3 is 75 numbers plus 1 bias. So there's 76 numbers per kernel. And we have 10 of those. So it's 760 total parameters. Now that's actually not very much. When you're talking about an input image that's 32 by 32, that's, I think, over 3,000 pixels. So even if you did like all pixels connecting to one neuron, that would be 3,000 connection weights you'd have to learn. Now, if it was 3,000 to 3,000 input pixels to, let's say, 100 hidden neurons, that would be 300,000 connection weights, right? So this sort of all-to-all connectivity uses way more parameters. The convolutional neural networks tend to be very economical in terms of the number of parameters that you use. So this is just to remind you that there's a bias. Each kernel has its own bias. It's not each neuron in the hidden layer has its own bias. Each kernel has its own bias. So by the way, I remember reading a paper and they're talking about the design of their convolutional neural network. We're going to use 3x3 kernels here, and we're going to use 32 5x5 kernels here, and all this stuff. And then they talked about a 1x1 kernel, and I was like, doesn't make sense to can evolve by a 1x1 kernel. That's kind of true, except that remember the sort of the convolutional aspect is throughout the two-dimensional image space, at least in the typical use of convolution kernels. It's sliding it over the 2x2 image. Now the depth-wise, through the color channels or through the channels wherever, those are not convolved. It's just fixed. So you never slide back and forth through the channels. You just take this slab and you kind of move it through the two spatial dimensions, and that slab drags around in the third dimension through the channels. So a 1x1 convolution, yes, it's this 1x1 kernel, but remember it's got this depth. In this case, it's got a depth of 64 numbers that you're moving around. So you're basically just taking linear combination of that little stack of values. Okay, so that's what convolutional neural networks look like. There are some exercises for you to work on, including some exercises that introduce you to PyTorch's treatment of convolutional layers. As you might expect, PyTorch has built-in convolution layers, both forward convolution and something I haven't talked about here, but let's say you want to make an autoencoder out of convolutional layers. So you'd have convolution down to some latent hidden layer, encoding layer. Now if you want to have the autoencoder decode that latent representation, you want to do a bunch of sort of unconvolution layers, right? So those are called convolution transpose layers. And turns out convolution and deconvolution are pretty much the same process. There are just some tiny little differences, and the convolution transpose layers know about those differences, so you don't have to worry about them and fuss about them when making your program. Have fun with it.